Sequences and Series Lesson 1. So we're going to start off by looking at the vocabulary and notation that we will be expected to use with work on sequences. So let's start with a very basic example of a sequence. I'm going to pick the sequence of numbers 2, 4, 6, 8, 10. So each number or object or item in a sequence is called a term, and you've come across that vocabulary before. So here's my sequence: 2, 4, 6, 8, 10, ... an infinite sequence. Now, a term you may not have come across previously is the word series. Now, a series is created when you add together each of the terms in a sequence. So if I added 2 plus 4 plus 6 plus 8 plus 10 plus all of the terms in this infinite sequence, I would create what we call a series. And it's important that we understand the difference between these two words, sequence and series. Now, we can label the terms in a sequence. So, for instance, if I refer to A1, that would be the first term, 2. If I refer to A2, I'm referring to the second term, 4. A3 refers to 6, the third term. So the little subscript number tells me which term in the sequence I'm talking about. I don't have to use A, I could have said U1 or T1. Now, if I want to refer to a general term in the sequence, I might refer to that as AN or AK or AR, etc. Now, in this particular example, AN, the nth term or the general term, is 2n, and you can see that because 1 times 2 gives you 2, 2 times 2 gives you 4, 2 times 3 gives you 6. So if n is the term number, then AN represents the term, and you can see that the term is calculated by doubling the term number. So this formula here allows us to define any term in the sequence. If you have a formula for the nth term of a sequence, you can calculate the value of any term in that sequence. Now, another piece of vocabulary that we are going to introduce is something called a summation. If we add together any terms from a sequence, we are creating a summation. So, for instance, we could write A1 plus A2 plus A3 plus A4 plus A5. And this is an example of a summation. Now, a very neat mathematical way of writing this is to use sigma notation, which you've come across previously in your study of statistics. Capital sigma means sum of. Now, I am summing the terms AK between k equals 1 and k equals 5. So make sure you look very carefully at the left and the right hand side of this and make sure you understand what this means. So this capital sigma here simply means sum of, or take the sum of. This means the terms, and the way that the sigma notation works is that you allow k here to take each of the values from the starting value in this case, which is k equals 1, up to the final value at the top here. And each time you increase the k value by 1. So we start with a k value here of 1, we end with a k value in the summation of 5. So we start with the first term A1, we end with the fifth term A5, and in between we simply increase the k value by 1 each time, which means we're adding in the second term, the third term, and the fourth term in our summation. Now, sequences can have an infinite or a finite number of terms. A sequence with an infinite number of terms is called an infinite sequence. So, for example, if I have a sequence that looks like this, 1, 2, 3, 4, 5, dot, 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 the dot, dot, dot indicating that this sequence continues, this is what I would call an infinite sequence. Now, if I decide to add together the terms of my infinite sequence, I create an infinite series. Remember, a series is created when we add together the terms of a sequence. So for the example above, if we have 1 plus 2 plus 3 plus 4 plus dot dot dot, so adding together the terms of the previous infinite sequence, we create an infinite series. Now, we can also write an infinite series using the sigma notation from up above here. We could write, for instance, sigma ak between k equals 1 and infinity. And this means we're adding together all of the terms of an infinite sequence. So creating an infinite series. Now at this point, very rightfully, you might be thinking, how on earth do you add together an infinite number of terms to create an infinite series? But this will be revealed shortly when you do a little bit more work on sequences. So we're now going to have a look at two different ways of defining a sequence using formulae. Now, the first way is to use an nth term type formula, such as this. So AK equals 4k plus 5, which allows me to calculate any term in the sequence. I could have used n here as well. I could have written an equals 4n plus 5 or ar equals 4r plus 5. You will come across lots of different types of example using different letters as the variable, so do get used to this. So this is sort of like a general term and allows me to calculate any term in the sequence. So this type of definition is called deductive or algebraic definition. So if I wanted to work out the 99th term in the sequence, so that would be A99, I would work out 4 multiplied by 99 and then add on 5, which would give me an answer of 401. Now, the second type of definition that we will look at is where we use an iterative formula. So an example of this would be a k plus 1 equals ak plus 4. Now, you've come across iteration and iterative formulae back at GCSE. This allows you to start with a given term and then calculate subsequent terms. So AK refers to a particular term and a lowercase k plus 1 refers to the next term after the term you start with. So we have an example here, AK plus 1 equals AK plus 4, which means to generate the next term, you take your current term and add 4. Now this process will only work if you have a starting term, so I would have to include information such as A1 equals 0, A2 then equals 0 plus 4, which is equal to 4, A3 then says take the previous term, A2, which is 4, and add 4 to it, which gives us 8, and so on and so forth. So you can't generate any particular term, but you can generate the next term. So for instance here, I can't calculate the 99th term unless I know the 98th term, which would mean I'd need the 97th term. So in that respect, it's less useful to use this type of definition because this only allows you to generate term after term after term. It doesn't allow you to pick out a particular term in the sequence and calculate it. So this process is called iterative or sometimes inductive definition. So we're going to pause here and have a look at a few very basic examples. So to start with, a sequence has nth term given by an equals 10n plus 1, and we're going to find the first 5 terms of the sequence. So this is really easy. This is algebraic definition. It tells us that a term is equal to 10 multiplied by the term number plus 1. So we'll put the answers up over here. A1 is equal to 10 multiplied by 1, 10 plus 1, which is 11. A2 is equal to 10 multiplied by 2 plus 1, which gives us 21. A3 equals 31. A4 equals 41. A5 equals 51. Now you'll notice that there's a difference of 10 between each of the terms, and this is a linear sequence, or sometimes what we call an arithmetic sequence, and we'll come on to types of sequence a little bit later on. Now, part 2, this is all about understanding the sigma notation here. So this tells us we're taking the sum, the sigma, of the terms from this sequence. So there's the an referring to the terms of this sequence. This means we start with the first term and we end with the 5th term in our summation. Remember, summation means to add together the terms of a sequence. So this means we are working out A1 plus A2 plus A3 plus A4 plus A5. We have the values of the terms up over here in red. We add them together, we get a total of 155. So, example 2. A sequence is defined by an iterative formula, which we're given here. We need to find the first 4 terms of the sequence if A1 equals 2. Well, we already have the first term, so that really means we need to find the next 3 terms of the sequence. The iterative formula here tells us that the next term is 2 times the previous term and then add 3. So this means that A2 will equal 2 times the previous term of 2 plus 3, which gives me 7. A3 will equal 2 times the previous term of 7 plus 3, which gives me 17. And A4 will equal 2 times the previous term of 17 plus 3, which gives me 37. And I have my first 4 terms of the sequence. We are going to finish off by introducing 5 pieces of vocabulary which can be used to describe different types of sequence. So first of all, very simply, an increasing sequence is a sequence in which each term is greater than the term immediately before it. So an example could be something like this: 2, 4, 6, 8, 10. A very simple example of an increasing sequence. Now, a decreasing sequence, again, very simple type of sequence, each term is less than the term immediately before it. So, for example, if we have 20, 10, 5, 2.5, this is an example of a decreasing sequence. Now, let's look at the next 2 pieces of vocabulary. So, first of all, we have a convergent sequence, sometimes also called a converging sequence. And I'm going to start by giving you an example of a convergent sequence. 2, 1, 1/2, 1/4, 1/8, etc. Now this also happens to be a decreasing sequence, but we're not really focused on that here because it's actually much more interesting that this is what we would call convergent or converging. Now in a convergent sequence, the terms are getting closer and closer and closer to a particular value. Now in this case, you can hopefully see that if you start with the first term of 2, you're dividing it by 2 to get the second term of 1, you're then dividing by 2 again, and you consistently divide by 2 to generate each new term. The terms in this sequence are converging to what we call a limit of 0. Now, they're never actually in this sequence going to get to that limit, because if you're starting with a value and dividing it by 2, you will always be left with some number. You can't divide a non-zero number by 2 and get 0 as an answer. So ultimately there will always be a value to each term in this sequence, but the terms will get smaller and smaller and smaller and smaller, and they will get infinitesimally closer to 0 as you generate each new term. So in a convergent sequence, the terms of that sequence approach a limit, or they get closer and closer to a limit. Now in this particular example, the sequence is converging to a limit of 0, or the terms of this sequence are converging to a limit of 0. That is not the case in every convergent sequence. Please be aware the limit is not necessarily always 0. Now in a divergent sequence, sometimes also referred to as a diverging sequence, we have the opposite situation to a convergent sequence. So for instance, if we had something like this, 2, 4, 6, 8, 10. Now we can see that clearly the terms are not approaching any particular limit, so we have no convergence, which means the sequence is diverging. Now it happens also to be an increasing sequence, but you could get a diverging decreasing sequence. For instance, if we had 2, 0, -2, -4, -6, this is diverging, but it's also decreasing. Now lastly, we have the word periodic. Now a periodic sequence is a sequence that repeats itself at regular intervals. So let's write down an example of a periodic sequence to illustrate this. So here's my example. My first term 0, second term 1, third term 5, fourth term 7, and then my fifth term is 0 again. My sixth term is 1, my seventh term is 5, my eighth term is 7, and then my ninth term is 0, and the sequence repeats itself again. So you can see this pattern of 0, 1, 5, 7 repeats again, 0, 1, 5, 7, and that's what makes the sequence periodic. Now this particular sequence would have what we describe as a period of 4 in this example, which is the number of terms before the sequence starts to repeat itself. So we're going to finish off by having a look at a few examples involving different types of sequences and ways of defining them. So question 1, a sequence is defined by u1 equals 2, and we are given an iteration formula here. It then asks us to calculate the sum of the first 4 terms here. So in order to calculate the sum of the first 4 terms, I need to know what these terms are. So we're given u1 is equal to 2. The iteration formula tells me that u2, or the next term in this case, would equal 10 divided by the previous term squared. So that's 10 divided by 2 squared, which is 2.5. u3 will then equal 10 divided by 2.5 squared, which comes to a value of 1.6. And then u4 is equal to 10 divided by 1.6 squared, which equals 3.90625. Now, to then calculate this, the sum of these terms, we simply add together 2, 2.5, 1.6, and 3.90625. This gives us a total of 10.00625, which is the value of the summation. So let's take a look at example 2. So the first part of the question wants us to evaluate a summation, and we're given the formula in this format here. Now, this part of the summation here tells us the nth term of the formula, or in this case, the rth term of the formula. So AR equals 1 over r minus 1. Now, we have to start with the second term and go up to the fifth term. So what we're adding together is A2 plus A3 plus A4 plus A5. Now, how do we work out these terms? Well, in the summation, we're given the sum of 1 over r minus 1, and that's the formula that allows us to calculate any term. So A2 is 1 over 2 minus 1, which is 1. So I'm replacing r by the term number. A3 is 1 over 3 minus 1, which is a half. A4 is 1 over 4 minus 1, which is 1/3. And to finish off, A5 is 1 over 5 minus 1, which is a quarter. So this summation is simply equal to 1 plus a half plus a third plus a quarter, and that comes to a total of, so this comes to a total of 25/12. Now, part 2 involves a little bit more thought. Express the series 2 times 3 plus 3 times 4 plus 4 times 5 plus 5 times 6 plus 6 times 7 in the summation format. So just to provide a little bit more clarity, let's put in some brackets here. They serve absolutely no mathematical purpose whatsoever, but they may actually help with working out what's going on. So we need to express this in the format of a summation, which means we need to see what the formula is for each term. Now they tell us to start with r equals 2, and you'll notice a 2 over here. So if this was r, then the 3 next to it would be r plus 1. And you can see that's common to each multiplication here. The second part of the multiplication is 1 more than the first part of the multiplication. So the formula f of r is r multiplied by r plus 1. So each term in the sequence is generated using this formula f of r, which is r multiplied by r plus 1. And you could think of this as the term generator here, AR. Now have a look at that. You can see that if your R value is 3, then your R plus value is 4, and you're multiplying 3 and 4 together. So we would write sigma R bracket R plus 1, and R equals 2 is our starting value here. Now we also need to find the value of R for which we stop calculating, and that's over here, it's 6. So we have 6 at the top here. So A is equal to 6 and f of r is equal to r multiplied by r plus 1. Now to satisfy yourself that this is correct, write out the terms of this summation and you will find you generate this result up here. Example 3. Sequences A, B and C are shown below. They each continue in the pattern established by the given terms. So part 1, which of these sequences is periodic? So you need to look for a pattern of repetition here, and you can see that C clearly is periodic, and hopefully you can see the repetition 25/1, 25/1. It in fact has a period of 3 as it repeats over 3 terms. Now, part 2, which of these sequences is convergent? So we've established the periodic sequence. Which of these sequences is convergent? So we're looking for a sequence where the terms get closer and closer and closer to a particular value. Now in A, that's clearly not happening because you're doubling the terms, so that means that each time you'll be generating terms that are bigger and bigger and bigger. But in part B, you are generating a convergent sequence, and you can see that the terms are converging to a limit of 0 in this case. And the last example, example 4, find the numerical value of this summation here. So we're starting with a k value of 2 and we finish with a k value of 5. So this means we need to input each k value into the formula: 2 cubed, 3 cubed, 4 cubed, up to the last value of k, which is 5, as we can see from the value at the top of the summation. And then we simply need to use our calculator to add these numbers together. So 8 plus 27 plus 64 plus 125 gives us a total of, and this gives us 224.